Good day, guys. Ever wondered how a carbon-carbon single bond, a carbon-carbon double bond, or a carbon-carbon triple bond is formed? Well, in this video, you will learn about the bonding and the shapes of organic molecules. First, let's get into the bonding. With respect to carbon, there are two main types of bonds. We have a sigma bond and a pi bond. Now, how are these bonds formed? A sigma bond is formed from the overlapping of two s orbitals. Recall the shape of an s orbital. Remember, an s orbital shape is that of a sphere. Also, a sigma bond is formed from the overlapping of an s and a p orbital. And lastly, it is formed from the overlapping of two p orbitals. So this is the head-on overlap. You can think of it like two cars crashing into each other. So when this p orbital and this p orbital overlap, they form a sigma bond. Now the second carbon bond or main carbon bond is a pi bond. And how is it formed? It is formed rather from the lateral and sideways overlapping of a p orbital, of p orbitals. So this is side by side. We can also visualize it now like two cars standing beside each other, not face to face, like side by side. Yeah. So when these two cars overlap, or these two bonds overlap, we get a pi bond. Now let's get back to bonding. Bonding occurs in three main phases. The first step is the change in the energy state of the carbon atom. The second is hybridization, and the last is the overlapping, or the bonding proper, if you can say that. Now, so let's get into it. So the first one, change in the energy state. We recall the electronic configuration of a carbon atom. A carbon atom has 6 electrons, and its electronic configuration is given by 1s2, 2s2, 2p2. So if you want to draw it in box notation, it resembles this structure here. When a carbon atom gains energy, one 2s electron is promoted to the 2pz. So as you can see here, in your 2s, you just have one electron, no longer two. One has been promoted to the 2pz. Hence, you have 4 orbitals. 1, 2, 3, 4. 4 orbitals of same electron capacity. It's possible for bonding to take place, but there is one requirement left, that is energy. The energies of the orbitals which are to be mixed or to overlap during the bond must have similar energies. So another process has to take on, and that is where we come up to hybridization. Now, what is hybridization? It is a mixing of atomic orbitals to form new orbitals called hybrid orbitals. So this, from the name hybrid orbitals, you know it is formed from two or more orbitals. Now these hybrid orbitals, they have similar energies and electron capacities, a requirement that is essential for bond formation. Depending on the type of hybridization taking place, we are going to get different types of carbon-carbon bonds. Alright, so let's get into it. The first hybridization we will look at is the sp3 hybridization. Now, what does sp3 look like? Now, I'm going to give you a trick here to easily know the number of orbitals involved in hybridization. To know the number of orbitals participating in a particular hybridization, you simply count the numbers above the s and the p. If you see no number before the s, it is a 1. So we have 1 s orbital and 3 p orbitals. Hence, in this excited state here, we are going to have 3 of this, so 1 s orbital and 2s and 3p orbitals are going to participate in this mixing up. So these 4 orbitals are going to mix up to form 4 new orbitals called sp3 orbitals. All right. Now, how are they arranged? They are arranged. Now, how are they arranged? They are arranged directed towards the four corners of a tetrahedron. So if you have this, now, if you have two carbon atoms which are sp3 hybridized, that is, they have sp3 orbitals. If you have these carbon atoms, if some of these orbitals overlap, what do we have? So we have this carbon and another carbon atom. If you look at this, we just have one overlapping here. So we just have one bond. And now these other sp3 orbitals here will be free to bond to other atoms. So here you can have it bonding to hydrogen, to chlorine, and many other atoms. Hence, so if it bonded to a hydrogen atom, we are going to have this, and this compound is called ethane. All right, so we see that sp3 hybridization results in the formation of carbon-carbon single bonds. All right, let's move on to the next. Moving to sp2 hybridization, it is similar. So we count the number of atoms needed for this hybridization. We have 1s, 2p. So therefore, just these 2s and 2 orbitals of the p are going to be used for bonding. So we have just these 3. So the pz, remember, a p has a p orbital, has the x, the y, and the z. So for an sp2 hybridization, just the x and the y will be involved. The z is unaffected. So therefore, we form 3 new orbitals, 3 sp2 orbitals. And how are they arranged? They are arranged with bond angles of 120. Like, you can think of it like, no, I cannot think of it. So we form 3 sp2 orbitals. Now, so if you look at it, we have, what do we have? We have 3. So these are the sp2 orbitals, and the shaded one is the pz orbital. So the pz remains unaffected. It still has its double lobe-like shape, and these are the other sp2 orbitals. So looking at this, let's try to get the resulting compound here. So we have carbon, carbon. The overlap of 2 sp2 orbitals forms what? A single bond, or one bond, yeah. And also, now if you look at it, we see that this pz and this pz are also free. They are standing sideways, so they can also overlap to form a pi bond, like we earlier saw. So we have another carbon-carbon bond, and these other sp2 orbitals here can now bond with other atoms. So they can bond with carbon atoms or other atoms. So therefore, we have, assuming the bond with hydrogen, we're going to have something like this. So we have ethane, voila. Now, if we look at the structure of each carbon atom, we see that this carbon atom, it has bond angles of 120 degrees. Like, you can look at it from here. This. The angle here is 120 degrees. So the bond angle for an sp2 hybridization is 150 degrees. Lastly, we look at the sp hybridization. So from the name sp, it means we have one s orbital participating and one p orbital participating. So in the excited state, just the 2s and the 2p are going to be used. So these are going to be used to form an sp orbital. So we're going to have what? 2s p orbitals, and we have what? We also have the py and the pz orbitals unaffected. So when these two sp orbitals are formed, they are oriented linearly, so they have a bond angle of 180 degrees. So if we are trying to get the structure formed after these two bonds, so we have carbon, carbon. First, we have two sp orbitals overlapping. That forms one bond. Next, we have shaded in blue is the py and shaded in black is the pz. All right. So these two, this py here and this py also overlap since they stand sideways. Voila. So they form another bond, which in this case is a pi bond, and similarly this pz also bond to form another bond, and we are left with just this one and this one. So these ones can bond with other atoms, so they can bond with hydrogen and also hydrogen, and this compound is ethyne. Now if we look at each carbon atom, we see that the bond angle here is 180 degrees. So the bond angle